In our everyday world, physical boundaries are absolute. If you throw a tennis ball and it hits a solid brick wall, it violently bounces back. Under the laws of classical physics, overcoming an obstacle requires kinetic energy. If you don't throw the ball with enough force to break the wall or clear the top, it stays on your side. The ball will never, under any circumstances, pass directly through the solid structure of the bricks. But this certainty is limited. It is a rule that only applies to the massive scale of objects we can see and touch. When you scale down past the surface of those bricks, descending into the microscopic void of individual molecules and atoms, common sense shatters. Down here, the predictable laws of classical physics stop working entirely, replaced by mechanics that allow for events that are impossible in our larger world. At this microscopic level, subatomic particles like electrons and protons do not act like tiny solid tennis balls. They lack fixed, rigid physical boundaries. If we look at this animated diagram of an electron, we can see it isn't a fixed point. It exists as a probability wave, a fluid state that maps out the mathematical chances of finding the particle at any given spot. The tallest peaks show where the electron is most likely to be located. As you look toward the outer edges, the ripples fade, representing a significantly lower mathematical probability. Because the particle exists in this state of mathematical chance, its physical location remains fluid until it actually interacts with a boundary. In this diagram, we see what happens when that probability wave confronts a microscopic energy barrier, a wall it lacks the kinetic energy to climb over. At first, it behaves exactly as we expect. The vast majority of the wave crashes against the wall and reflects right back. But the leading edge of the wave doesn't stop. It decays rapidly while it bleeds directly into the solid thickness of the barrier. If that physical wall is thin enough, a minute fraction of the wave survives the journey and emerges on the other side. Because a piece of the probability wave made it through, there is a physical chance that the particle will vanish from one side of the solid wall and instantly materialize on the far side. It didn't break the wall, and it didn't go over it. It bypassed the physical obstacle entirely by phasing straight through, an act known as quantum tunneling. This mechanical quirk is what allows stars to shine. We can see its consequences in the core of our sun. The sun is powered by nuclear fusion, a process where hydrogen protons smash together to create helium, releasing massive amounts of heat and light. Protons carry a positive charge, meaning they strongly repel one another. Even at the extreme temperatures inside a star, they lack the classical energy required to overcome this repulsion. They manage to fuse anyway because their probability waves reach out and quantum tunnel through that invisible barrier of repulsion. Without this microscopic rule breaking, those protons would continually bounce off each other, stars would never ignite, and the universe would remain dark. Human engineering has moved beyond observing this phenomenon to actively using it. Every time you save a photo on a smartphone, you use flash memory. This technology works by trapping electrons inside tiny, isolated compartments. To write or erase that data, we apply a specific voltage that coaxes those trapped electrons to tunnel straight through the solid insulating walls holding them in. Researchers also use this probabilistic bleeding effect in scanning tunneling microscopes, mapping and manipulating individual atoms with precision. Smartphone storage and atomic scale imaging are both possible only because we can manipulate particles that ghost through solid physical barriers. It shows that reality, at its core, is not rigid. It is a fluid, probabilistic architecture that works differently than the world we see.